Alright, y'all. Now it's time to explain these things called lemniscates, which are when you have an r squared equals, and then the roses, which is where it's just r equals. And these have multiple angles. Now the lemnistics don't have to have multiple angles. If you remember yesterday, I gave you one where it didn't, but these both have multiple angles. Roses always have multiple angles, and that's just the nature of how you get the petals. So anyway, so take the square root, so the 25 becomes plus or minus 5, and again we're excluding all the areas where the signs are negative, because we can't take square roots of negative, so everything below. Now you may ask, well, why is that there? And it's because of the multiple angle, right? So we're only interested in the maximum distance for the petals, which means we're going to get 5 times 1. And that only occurs when the angle is at the pi over 2 location. So that's why I'm doing this. And so we get, again, we got to do our generalized solutions. And so these are the two locations where we get the sine values of 1. And they just happen to be 180 degrees, right? So pi over 4, 5, and then also negative 5, which maps here, and then 5 pi over 4, 5, and also negative 5, which maps back on there. So the negative radiuses map back on to the other side, since these are opposite quadrants. Same thing occurs here. This is cosine, however. So you take the square root, you get plus or minus 6, and then we want the maximum distances, because that's the edges of the petals, so we want 6 times 1, right? And again, we can't take the square root of negative 1, so we're excluding the negatives from the cosine. So we only care about 6 times 1, which happens at 0. So that's why I'm doing this. And then when you divide, you get pi k. Okay, which means 0, pi, and 2 pi. So plus or minus 6, so at 0 you get 6, and then negative 6. And then at pi you get 6, and then negative 6, and then 2, and so forth. So again, once again, the negative radii map back on the other. Okay, and then the roses. Now, there's ways of doing roses. With me, I think it's easier to go ahead and break this up. So again, once we get 3 times an angle equals 360, we've completed an entire cycle. So we're going to get 3 cycles within the 0 to 360 interval. What's the period? 120. That's why I'm dividing by 3. When does this equal 360? So every 120 degrees, we go through 1 unit cycle. Each unit cycle is divisible into 4 quarters, so 30. So all the angles that are going to create the quarters within each of the 3 unit cycles, we can create by adding 30 starting with 0. And so here's the first unit cycle. It ends at 120, because that'll be 3 times 120, which is 360. The next unit cycle, again, these are still angles less than 360, so we have to include them in the domain of solutions. Okay, ends at 240, which is still a multiple of 360. And then again, the third unit cycle that occurs, again, these are all angles that are still less than 360, so we got to include them in the domain of the solutions. Okay, and so notice that this would be 0, 30, 60, 90, 120, and then 150, 180, 210, 240, and then 270, 300, 330, 360. But all we care about is the maximum distances of the petals. That's all we care about, and that happens when the cosine is 1 or negative 1, which would be these locations. Now when it's negative 1, you get a negative radius. So this can map 180 degrees in the other direction, and it's good to know where those are, because if they are mapping back like they were up here, then it's not an extra part of the graph and you only have 3 petals. But if they map onto something else, then you have 6 petals. So that's why I'm doing this. And it turns out that those are the same angles as here, which means they map back. So a negative 5 radius up here maps back to this. a -5 radius over here, which is 180, maps back to this, which is 0. A -5 radius over here, which is 300, maps back to this. Okay, so then these are the directions when the radius is 5. So it's 0, 120, and 240, and then just do your little loop-de-loop. Same thing here. This time you're going to have 2 unit cycles, and so every 180 degrees you go 1 unit cycle. Each quarter is worth 45, and so then you just create, so from 0 to 180 is the first unit cycle, 2 times 180 is 360, and then from 180 to 360, which is, again, you have to include because those angles are less than 360, so they have to be part of the domain of the solution. All right? And we're still talking about the cosine, so we're only interested in the maximum distances from the petals, so when the cosine is 1 or -1. It's 1 first part of the cycle, and then after the second quarter of the cycle, it's -1. So positive radius, negative radius. All right, well, 180 degrees, where would these be pointing at? Well, 270 and 90, which are not the same as these, so we got 4 petals instead of 2. Right, so 0, 180, 90, 270. 0, 180, 90, 270. Isn't that cool? I've always thought roses were cool. Now, my method makes it so much quicker. So, I came up with this, I don't know how long ago, but thank God, it makes it so much quicker. And you guys got some more of these. So again, I gave you the solutions. This is the one I gave you in class, and I tried to color code it. We got green over here and red over there, because since it's 5 theta, it's still the same intervals. It's just the maximums are occurring at different locations, because at cosine, it's the first and third quarter, right here. And sine, it's the second and fourth quarter, right here. Right? And these cases, when you add and subtract it from 180 to see where the negative radiuses point. Right, again, if it's bigger, you subtract 180. If it's smaller, you add 180. Right, and they happen to be the same as the ones that were over here. So you only have 5 petals, not 10. Okay, and here's the spiral. Now, the spiral I gave y'all, or explained yesterday, was just meant to get the idea across without getting cumbersome with the numerical values. So this one, it's a little cumbersome because you got to multiply 3 times the angle. And imagine if you're using degrees, 3 times 30, the first one, you're already at 90. 3 times 60, 120. 3 times 90, 180. So the scale, you'd have to scale it. You could do it, but this is another reason why maybe radians is a good idea. So I went ahead and I used 30-degree intervals, which is pi over 6 intervals. I went into the TI calculator. I set up a table based upon the 3x. So you guys can see that, huh? Yeah. Sorry, it's sideways. I'm kind of on a table here. But you can see the 3x. And then I went to the table set, and I set it starting at 0, and then I did, let me set it starting at 0. And then I did, what did I do? Pi divided by 6, which will change to the decimal that you saw there, right? Okay, so now we're good to go. So then we just go to the table, right, table, and we got these numbers. And so that's what those are. I use this. And you don't have to write them down. You can just scroll as you go around every 30 degrees. Just write those y values. Okay, so I just started the table, and so, right, 1.57, and when it's pi over 6 or 30, 3.14 when it's pi over 3 or 60, 4.71 when it's pi over 2 or 90, and then when it's 2 pi over 3, or 120, it's 6.28. And then at 150, or 5 power of 6, it's 7.85. And then at pi, or 180, it's 9.42, which is a little bit shy of 10. And then again as you go around. So that's called a spiral. Alright, now I just got off the phone with, well, let me make a new video of that.